thank you for the welcome, and thank you for the introduction, and thank you for the invitation. So there used to be two groups, one at Oxford and one in Moscow. And then, unfortunately, for all of us, the Moscow group doesn't exist anymore, really. But now we have a startup enterprise doing optical neural networks, which is one of my topics. In fact, there'll be three topics. If you fall asleep during one of them, feel free to wake up. They're completely unrelated to each other. The first one is the most complex. The second one is easier. The third one is somewhat complex as well. So optical neural networks. Well, I guess I don't need to argue that machine learning is taking over the world. I like to make this statement, which I think becomes, with time, becomes less and less controversial. I like to say that machines generally performs better than humans in all environments that they're fully aware of. Right? So they can calculate integrals better than us, they can recognize faces, they can play chess, play Go. The only environment in which machines are not performing better than us is our natural environment. Robots are still not as good as humans, for better or worse. We'll come back to this topic, but for now, I just want to say that machine learning is powered by neural networks. And for those few of you who are not aware what a neural network is, I want to give a really very short 2-minute tutorial. So suppose you are facing a task of given a bitmap, and you have to find out if it's a cat or a dog. Right? Well, what is it mathematically? Mathematically, it can be interpreted as a function. Right? The input is a bitmap, which can be interpreted as a vector, even though it's two-dimensional, it's still a vector. And then the function determines the probability of it being a cat or a dog. So it's basically a one-valued to two-valued function as a function of a vector. And apparently, our brain is quite good at calculating these functions. The question is, how can we get the machine to calculate the function? The answer is that we construct a structure that looks as follows. We start with the input vector, and then we take some kind of matrix, which is called the weight matrix, which we can adjust, and we multiply by that vector. So we obtain a product here, and then to each element of the product vector, we apply a so-called activation function, some kind of single-valued nonlinear function. So, for example, hyperbolic tangent is a popular activation function. Right? This one we don't train, we don't change, it stays constant. And then we repeat this many times. That's why it's called deep neural network, right? So layer 1, layer 2. So output vector gets multiplied by another weight matrix. Layer 3, layer 4, layer 5. In this case, it has only two outputs because of the function is two-dimensional. And that's basically a neural network. And there's a mathematical theorem that any arbitrary function, however complicated, can be well approximated by such a structure. Provided, of course, that the weight matrices are correct, which constitutes training of neural networks, which we'll discuss a bit later. For now, let me say that, as I said, machines seem to be taking over the world. Well, it's not exactly true, because digital electronics is supremely inefficient. If we compare the performance and the efficiency of digital electronics with the brain, we see, well, the performance, the speed is kind of become comparable, but the energy efficiency is still a few orders of magnitude below, right? And this inefficiency is really becoming noticed nowadays. Nowadays, about 2% of the world's electric energy is used by data centers, right? And this number is growing exponentially. In some countries like Ireland, it's as high as 7%. So really, very, very soon, we are going to hit the brick wall. And for better or worse, if digital electronics remains in control, machines are not going to take over the world, right? Now, if we ask ourselves for some intuition why digital electronics is so slow, the answer is easy to find. It's because of its digital nature. As I said, the most complicated, the most computationally heavy operation in machine learning is vector matrix multiplication. Now, if you just take two real numbers, two 32-bit numbers, and try to multiply them by each other, it's 1,000 single-bit operations. and each such operation is a non-trivial physical process. And in a neural network, there are trillions of such operations. So of course it's going to be inefficient. In the brain, on the other hand, the whole matrix vector of vector-vector multiplication, the whole vector-vector multiplication is a single physical process, right? So then the neuron collects the input vector via the dendrites, then multiplication occurs in the body of a neuron. If the result of multiplication is above a certain value, then there is an activation spike, which is transmitted down the axon. So it's a single analog physical process. And then the natural question to ask is then, is there a technologically accessible platform that allows us to do neural networking like this and not like this? And the answer is, yes, there is. It is optics. So optics, namely interference and diffraction that occurs in propagation of light, can actually implement matrix vector multiplication quite efficiently, as we'll see in a few next slides. And then, well, theoretically, with optics, you can like with the current state of technology, more or less current state of technology, you can obtain both the speed and efficiency that is better than that of the brain. Now, this is the current state of technology. It shows that there are two options for realizing an optical neural network, either free space or integrated. Now, obviously, this is much, much more appealing, right? Because you don't need to align this. You can produce it at the factory. It's quite much smaller in size. So this is nice. The bad news for the integrated circuit and good news for free space implementation is that the dimension that currently can be integrated in an optical integrated circuit is on a scale of maybe a dozen units per layer, something like this, maybe a couple of dozen. Here in free space, on the other hand, we can go up to hundreds and thousands. So this technology is much more mature, and this, I would say, if we want to really have a practical neural network today, then we should use this approach, and tomorrow we'll be using this approach. Now, I mentioned the numbers. I want to justify the numbers. So I said 10 power 16 operations per second. Where does it come from? Well, think of it. Let's say we have a weight matrix of 1,000 by 1,000, which means 1,000,000 operations. Vector matrix multiplication is 1,000,000 operations, right? Now, the input vector is supplied to the network via electro-optical modulators. Reasonable bandwidth is 10 gigahertz, 10 power 10. And that's where 10 power 16 comes from. Now, where does 10 power 17 joules per operation come from? Also easy to explain. What we need is a reasonable number of photons in each output vector. In each element of the output vector, right? Otherwise, we have too much shot noise. That means that in principle, we can have less than 1 photon per operation, because you see, we have 1,000 outputs, but 1,000,000 operations. So we can have less than 1 photon here and still have a reasonable number of photons here, as was shown in this paper, right? But of course, if you want reasonable noise, then it should be like 10 power 4 photons per output, 10 power minus 14 of a joule, and that means per operation 1,000 times less, 10 power minus 17 of a joule. So that's where the other number comes from. So you see, simple argument shows that optical implementation can be very efficient. And again, compared to digital electronics, this is a newest NVIDIA machine, 10 power 14 operations per second at the very, very, very best. And the efficiency is 10 power 11 operations per joule, so 6 orders of magnitude poorer. Now, how to implement matrix vector multiplication? The idea has been around actually, almost for as long as neural networks have been known, for like 50 years. This is a simplified version. This is done by means of electro-optical modulators. But let's just assume for now that an electro-optical modulator is some kind of mosaic, right? A spatially variable absorber. So what you do is take your vector, right? So you impose your vector onto this rectangular laser beam, this elongated laser beam, the laser beam with an elongated spatial profile, right? And then you fan out each element of the vector onto a row of the matrix. And then you transmit each element of the vector through the matrix. So you get the product between the matrix element and the vector element. And then the last thing that remains to do the summation. So summation is actually most difficult. So to do the summation, you put this this lens, this spherical lens, which collimates the horizontal dimension, which was previously diverging, but focuses the vertical dimension, which was previously collimated. It focuses it, meaning it performs the Fourier transform. So in the Fourier plane, you then put a slit, which selects a zero spatial frequency. Yeah? Selecting zero spatial frequency in the Fourier image is the same as integration, right? And so that's where the summation comes from. So a very simple scheme, and it works. We've implemented it. I mean, it's been implemented before us, but we claim the largest dimension. So, of course, in practice, it's slightly more complicated, but the principle is the same. We use a spatial light modulator. So to produce a vector, we use a digital micromirror device. And for the weight matrix, we use a liquid crystal spatial light modulator, right? And then we look at the output signal with the camera. And the results look like this. Top row is theory, bottom is experiment. The first column is the input vector. The second column is the matrix on the liquid crystal SLM. And the third column is the element-wise product. And then you need to perform summation. And the summation looks like this. So this is your output vector, matrix vector product. And you can see that you have a reasonably good agreement between experiment and, well, between what you obtain optically and what you expect. By digital multiplication, we say it's about an 8-bit agreement. Our referees say it's 5-bit agreement, so we have to find a compromise. But yeah, so we can also do complex numbers. Matrix sizes we can do is up to, well, we published up to 1,000. In fact, we can do up to about 100. Freudian slip. 100. In the lab, we can do up to about 200. And the big question to ask then is the training of an optical neural network. Right? So what I've shown you now is one can do the inference. One can actually do the regular functioning of the optical neural network. It's the matrix vector multiplication. I've shown you activation function can essentially be any nonlinear optical effect, so also done easily. But the question is, how can we train it? And again, I'd like to make a step back and tell you what the training is. So training of a neural network is, again, finding those yellow weight matrices such that the deep neural network will produce the function that you want to see. How do you train it? Well, for training, you need a training set. That is, you need a number of input images, cats and dogs, and for each image, you need a correct answer, whether it is a cat or a dog. Right? So you need a few thousand, like up to 1 million of these. And then once you have the training set and you have your neural network set up, then you can calculate the cost function, which is the mean squared error between the neural network output, f of x, and the correct answer. And that's called the loss function, or the cost function. The good thing about the loss function is that it's differentiable with respect to the weight matrices. Meaning that you can apply gradient descent. You can calculate the gradient of this L with respect to W and apply iterative gradient descent to minimize the loss. And that's basically the training. Now, mathematically, the gradient looks quite simple. Of course, you can. One would think, like looking at this, remembering the complex structure of a deep neural network, one would think that calculating the gradient of each layer is a complicated task. But it turned out that it has a relatively simple mathematical form. Looks like this. The gradient of the loss with respect to each weight matrix is obviously also a matrix, which is an outer product of two matrices, of two vectors. outer product of two vectors. The first vector is the actual value of the neuron in the previous layer. The second vector is the so-called error vector, delta, which I'll explain now what it is. So the error vector, well, for the last layer, it is simply the difference between the neural network output and the correct answer. For each previous layer, to calculate the error, what you do is you take the error of the next layer, multiply each element by the derivative of the activation function, then multiply the resulting vector by the adjoint of the weight matrix, and you obtain the error in the previous layer, and then you go back to obtain yet the previous layer, and then the next previous layer, and all the way to layer 1. That's how you obtain the error vectors. It's a so-called backpropagation algorithm proposed by Jeff Hinton back in 1986, and that's basically what has given a start to the modern machine learning. So the question is, can we calculate the training signal optically? Well, okay, so before we do, I should say that the standard approach, obviously we're not the only group who is doing optical neural networks. The standard approach that people use is simply to model an optical neural network in a computer and calculate, train it digitally inside the computer, and then simply transfer those weight matrices that have been calculated digitally in silico onto the SLM. Now, this has two problems. One problem is that it's slow, right? Obviously, if we want the neural, we say that the neural network performs like 3 orders of magnitude faster than a digital one, and then suddenly we need to train it, and the training is still digital, then it's a problem. And second, it's quite sensitive to errors. What if our model is not perfect? Right? What if there is dust, aberration, and so on? Right? Obviously, we will not, the training would not be accurate. Now, there is a partial solution that we produced in this paper, which would be to take these neuron values from the optical neural network and take the error values from a digital one. You see, these ones are available by running the optical neural network. We have the neuron activation values, but then the backpropagation will have to be done digitally. And, well, it's a partial solution, meaning that it makes the neural network more robust to errors and noise, right? But of course, it's still slow. So that's not a complete solution. Complete solution would be to calculate the training signal all optically. That is, to determine also the errors optically. That is, to implement backpropagation algorithm optically. And that's what I'm going to show now. So if you look at the forward propagation for inference and backward propagation for training, you'll see that the processes are actually quite similar, right? So in both cases, well, here you multiply by the weight matrix, here you multiply by the adjoint of the weight matrix. And those of you who are experimental opticians will immediately tell that multiplying by adjoint of the weight matrix would correspond to simply transmitting the same vector backwards through the same interferometer, right? So by physically propagating the light backwards, you can actually perform this operation here. The problem arises here with the activation, because you see here, for the forward propagation, you need to apply the nonlinear activation function. For the backward propagation, on the other hand, you need to do something linear. You need to multiply by the derivative of the activation function. As of course, there are not many optical media which behave differently for forward and backward propagation. That would be nonlinear for forward and linear for backward. And, well, so again, the requirements are these two, and plus the value by which the backward signal must be multiplied. It must be the derivative of the activation function. So not just linear, but linear with a specific absorption. And very fortunately, we have found that there exists a particular nonlinear effect that does satisfy these requirements. The effect is saturable absorption, right? Well, I'll remind you what saturable absorption is. If you have a two-level system, right? You send weak light through the system, the atoms are sitting at the bottom, so the light will be absorbed. But if you send strong light through the system, a lot of atoms will be pumped to the excited level, so there'll be so stimulated emission will be almost of the same magnitude as absorption. As a result, the two effects will compensate each other, and absorption will be greatly reduced. So that's a nonlinear effect. It can be obtained both in free space, we use our favorite rubidium vapor cells, or we can do it in an integrated setting by using graphene. And well, and you make forward signal strong and backward signal weak, which, of course, weak signal will make everything linear, so this is nice. But then how about 3? How about requirement number 3? Well, it turns out that specifically for saturation absorption, for saturable absorption, requirement 3 is also satisfied, right? So it's satisfied. Well, here you can see here you can see the actual activation function, so 0 transmission for weak field, strong transmission for strong field. The derivative, the red curve, looks like this. The actual backward transmission looks like this, or you can rescale it, which of course will just correspond to a different learning rate, will look like this. Now, you see for weak fields, and we're primarily interested in weak fields, these curves are approximately similar. The orange curve is approximately similar to the red curve. Again, with approximation and only for weak fields, but this turns out to be enough. Before I show you the results, the experimental results, I should answer a question, the following question. Okay, so now we can do backpropagation, but how can we calculate the error in the last layer? Can we also do it optically? The answer is yes, because, well, it's a difference between the neural network output and the correct answer. And, well, you can do it just by interference, right? So you have the output of the neural network here, and then you send in a laser with the correct answer here, right? And then you subtract the two just by means of destructive interference. So that's the last layer error, and then you propagate backwards through our system. So the whole setup, actually, to be honest, we have not yet done this, right? We've done the subtraction digitally, but the setup looks like this, right? So you can see a neural network with 2 layers, right? One input layer, 3 dimensions, output layer, 2 dimensions, hidden layer, 5 dimensions. So you send in your signal here. Activation function is a rubidium vapor cell, right? You obtain the activation values of the first and second layers, and then for the error, you send in the error of the output, right? Propagated backwards through the second layer and through the saturable absorber, and you pick off both error here and here. You obtain 4 vectors, right? 2 vectors for the activation, 2 vectors for the error. You calculate the outer product, right? And this is your training signal. So, okay, what this picture shows is, well, this one shows the performance of the activation function. Again, for weak input amplitudes, this absorption is significant. For strong input amplitudes, it becomes less significant. And this shows the backpropagation. So this shows the amplitude of the backward signal as a function of forward input, right? And so what you see is that if the forward signal amplitude is weak, right, then the saturable absorber will absorb, so there will be no signal propagating. If the forward amplitude is strong, then the absorption becomes less significant. And you can see that the behavior, the orange curve, the experimental behavior, like the blue points, should be theoretically according to the orange curve, what it is. But what we really want is behavior according to the red curve. And we can see that the 2 behaviors are largely similar. And this suffices for our task. So this shows the training. So the task that we set is quite simple. We give our neural network a training set consisting of two sets of points. So for each point, the x and y coordinates are given. So what class 1 is this circle here, class 2 is the circle here, and the neural network should be able to distinguish, given an arbitrary coordinate, it should then be able to distinguish whether this coordinate belongs to class 1 or class 2. Different configurations, And you can see that the trained neural network performs reasonably well, right? So it can tell correctly that the center, that low values of coordinates belong to the blue class and high values of coordinates belong to the yellow class. Again, for different configurations. And here you can see the comparison with in silico training. And you can see that the digitally trained machine has error, neural network has errors, it does not perform as well. Here you can see the learning curve. So as you progress with the learning, your accuracy improves, your loss function decreases, and you can see the performance, right? So in the beginning of the training, the neural network makes significant errors. By the end of the training, it makes 0 errors. This is the video which I'll not show. And that brings me to the end of the first part of the talk. Maybe I'll take a break and ask if there are any questions. Yes, please.
So you mentioned, that in the beginning of your talk that, well, the goal is, to save the energy and implement the neural network at the lowest possible power. But here it looks like you're using saturated absorption as the activation function, which obviously doesn't work at like 100 photons level that you mentioned in the introduction. So is there any way to actually, get to your goal and...
Well, okay, theoretically it does. So theoretically it does because, well, of course it has to be slow, right? But if you calculate the number of photons, the saturation intensity and so on, well, to saturate an atom, you need just 1 photon. So in principle it does, in our experiment it doesn't yet.
There's a question here.
I want to ask a question regarding the training of the neural network. So you're opting for all pure optical training because in silico you can't model the noise and everything. Can I ask, when you have noise, do you have the problem of like vanishing gradients or barren plateaus when you're training these networks?
Well, we have not encountered the problem of vanishing gradients. We have not, because our neural networks are relatively simple. In principle, one can imagine that would arise. Which is, of course, another argument in favor of optical training.
Any other questions?
Okay, I'll proceed, and then you can think of more questions later. The second half is more, third is more fun. A robot aligning optical experiments. So some of you will be very happy to see it. Obviously, aligning a setup, this one might be familiar. This is Max Planck Institute, not our experiment yet. But a huge part of everyday work of an experimentalist is aligning this, right? Every mirror has to be aligned with the precision of with a micron precision. And the question is, can we assign this work to a robot? And well, what we say is that a large fraction of alignment work is mode matching, right? So making sure 2 beams are exactly identical to each other. So to model this, we build a March-Sander interferometer, right? Well, aligned means that this beam is matched with this beam. Misaligned means that the 2 beams are not identical. So again, they must precisely match in position, direction, width, and divergence. So 4 degrees of freedom. In fact, position and their direction is 2 degrees of freedom, so 6 altogether, right? Well, in this case, we have high visibility. In this case, we have poor visibility. And, well, on camera, if you put a camera at the output, then when alignment is good, it looks like this, right? When you change the path length difference with the piezo, you just see blinking, right? The 2 beams, there's either complete destruction or complete, either destructive interference or constructive interference. If the beams are not perfectly aligned, then you'll see something like this. You'll see fringes. So fringes means alignment is not good. And well, this is the experimental setup. So we have a March-Sander interferometer with 2 lenses to change the beam position and divergence. Beam width and divergence. We have a mirror here and a beam splitter, so all 6 degrees of freedom. And the camera takes the video from the video clip from the camera is sent to the reinforcement learning agent, which then sends command to motorized mirror mounts. Now, an important technical detail is that, well, again, those of you who are in the lab, in an optics lab, you've seen the piezo move like this. But the difference from a regular lab is that it's a sawtooth, but the sawtooth is asymmetric, right? Moves like. The reason is that this will tell the agent which way the beams are misaligned. Okay, let me explain this. So if you look at this picture here, if you just look at the fringes, the two beams are indistinguishable. So you will not know if the beams are like this or like this. You see, but the direction of the movement of the fringes, which is indistinguishable to us as humans, will tell the agent which way, which will kind of lift this symmetry rather. So that's why piezo movement is asymmetric. So to formulate this in the language of reinforcement learning, well, we have an environment, which is our system. The environment produces observation, which is the video clip from the camera. The observation goes to the agent. The agent has a certain policy according to which it chooses an action upon the environment. After the action, the environment will change its state and give a reward to the agent. So in our case, this is the observation as the video. The action is the movement of the four optical elements here, two lenses and beam splitter and mirror. The reward, well, naively, one should choose the visibility as the reward, right? One wants to maximize the visibility, therefore, visibility should be the reward. However, in practice, it's a bit more complicated because, again, experimentalists know that visibility of 95% and visibility of 98% is a big difference. So to make this known to the agent, we had this term of logarithm of 1 minus v, right? Shows that which really encourages small difference in final alignment quality. And then there is a penalty which prevents the agent from doing something really stupid, which means making actions which will completely misalign the interferometer, make one of the beams completely off the view field, which of course, if it happens, then no alignment can proceed. So then we give the agent a significant penalty. Right. Well, this is the information about training, which is probably not too important for the physics audience. This is kind of fringe pictures that we see. I mean, I should emphasize that in aligning mode matching with two lenses and two mirrors, right, when you have control not only of position and the direction of the beam, but also of width and divergence, is a difficult task even for a trained human expert, right? So a trained human expert will probably take at least half an hour to align such an interferometer. Right. Now, before I show you the results, I should say that, okay, I should come back to something I mentioned in the beginning. That, remember I said that the only environment in which machines are not yet better than humans is our everyday environment, is our everyday world. So robots are not yet as good as humans. Why is that? Can anybody tell?
Something unexpected comes up.
Something what?
Unexpected materials.
Well, no, not exactly. Even if the world is completely expected.
Awareness.
Sorry?
Awareness.
Awareness, no. Well, an agent can play computer games, for example, right? Computer games, a lot of unexpected things come up, and there is a lot of unawareness. No, the point is
the data that is trained on.
Yeah, that's right. That's right. So in a usual task like calculating integral or comparing faces or whatever, the training set is already available, right? So the machine can process thousands of elements of the training set within seconds. A robot, or think of a baby, right? When a baby learns to walk, right? They really get, like when a robot learns to walk, they really get a new element of the training set every second or so, maybe every large fraction of a second. So to collect the training set takes a very long time. And of course, the training, as the robot gets trained, the training set gets modified, right? So it needs to be recollected. And that's a huge problem. That's why robotics is so developing more slowly. Nowadays, there's a significant effort in this field to learn, to train agents on so-called imagined trajectories. So they obtained some trajectories through their experience, and then they have to imagine additional trajectories, model the environment, imagine additional trajectories, and then they have a larger training set, and then they can train themselves. But we don't use these advanced methods. We just train on simulated data. So we simulate our interferometer and, well, train our agent on the simulated data. But then another problem arises. The problem is that simulated data look like this, the experimental data look like this. So if you put the agent to this, that, you know, give this type of observation to the agent trained on these data, the agent will be at a loss. So the way it's done is by means of so-called domain randomizations. And that means applying various types of noise to the environment. That is, vary the beam radius, vary the brightness, add white noise to the pixel, randomize the piezo movement, and so on. So model all sorts of unexpected features that can occur in the environment. And then, if the agent is trained with these randomizations, it's actually quite good with these. So here you can see the experiment. As you can see, as I said, it was done in Moscow. So here, the TV crew was shooting. So here's just a small film that they made. This is a motorized mirror mount. And this guy actually didn't do the experiment. Right, so that's number one. And video number two, let me restart it. So you see the initial interference pattern, and now the agent performs actions, and that's now it's somewhat reasonably aligned. Right, now this slide here compares the interferometer with a human. And here I should say that this comparison was done in the old version of interferometer when we only operated mirrors. So we have no lenses, just the mirrors, right? And we also had discrete actions. And the comparison looks like this. The blue curve is the agent, interferobot, and the red curve is a human being. And you can see that the agent performs much better. And actually, it's interesting to look at different stages of the process. Here in the first stage, the interferobot starts moving. Remember, it's this symmetry that I told you about, right? The human will look at the fringes. They will not know which direction to turn the mirror. But the interferobot does. It will start immediately turning the mirrors and will do so correctly. The second stage, well, once the human had a chance to play around with the system, then they will quickly turn the mirror in the correct direction, so they'll get approximate alignment reasonably quickly. And the interferobot moves much more slowly and cautiously. And then finally, in the third stage, well, the final alignment is quite difficult for a human, but much easier for the interferobot. In summary, the interferobot wins by a large score. Now, this is another slide that shows, I want to boast, shows kind of intelligence of our agent. So alignment of the interferometer is kind of, can be kind of associated with climbing a hill, right? You have some starting point, right? And then you are allowed to move in certain directions, turn one mirror, turn another mirror, that's movement in certain directions, and then you're allowed certain step sizes, right? And you want to minimize the number of steps. And well, if you're dumb, you'll do something like this. You apply a greedy policy, so you'll make small steps, each of which will increase the height, the altitude. If you're intelligent, you will do something like this. Much fewer steps, but that means that you have to somewhat misalign the interferometer before aligning it much better. And now our agent does the blue curve, blue trajectory rather than the red trajectory. As can be seen here, for example, when you look at points 24, 25, 26. You see at point 24, it's somewhat reasonably aligned, but then it chooses to significantly misalign the interferometer, go to number 25, and then realign it by number 20 to point number 26, much better. So this corresponds to the technique of walking the beam that we teach our graduate students when they first come to the beam, to the lab, right? Walking the beam, and that's and the agent has learned this technique on its own. And that concludes my second part. And again, I'll pause and ask for questions. Yes, please.
Thank you. You showed that to train your reinforcement learning agent, it takes about 26 hours on a 2080 RTX. So can I ask what happens when you have a trained agent, but you want to try aligning on different setups? Do you have to?
Hopeless.
You have to train again.
Yeah, after you train.
Okay.
Sorry, just a fun question. The human versus this is a silly question. The human versus the agent, right? There was a 5 minutes time limit I saw or something like this. What was the reward for the human then, right?
A paper. So the reward was actually negative because the human performs better. Well, so hopefully the human agent still was somewhat honest.
Okay, yeah.
Well, I guess, the reward was still positive because they don't want to disgrace themselves in front of their peers, right? Anyway, okay, last part of the talk, which I actually presented here online.
One last question.
Yes.
One more question. So the agent will learn as good as the data is, as we noticed earlier, right? So, and this is a classical agent trying to optimize a classical experiment.
That's right.
People have tried to do classical agent for quantum experiments as well, using superconducting qubits or other things. Have you tried to go to the quantum regime here, and what would you expect to see? Like what
we haven't, but in principle, it's entirely imaginable. So so of course there is a lot of, even like we had this experiment on single photon tomography, which required optimization of efficiency, which is kind of turning a lot of knobs and spending hours just turning knobs trying to increase a single parameter. So one can imagine this being assigned to a robot like this. Okay, third part. So third part I already presented here online a year or two ago, so I will go a bit faster. So it's about overcoming Raleigh's limit in imaging. You know about Raleigh's limit, right? You know that if you try to image something, then there will be diffraction on the objective lens, and a single point will become, the image of a single point will be something like this, a blur called point spread function. So if there are 2 points that are close to each other, they'll coalesce and you will not be able to distinguish them or measure the distance between them. And improving the resolution, resolving this Rayleigh curse, what they call, has been sort of a quest of microscopy for many years. People have come up with two techniques. Many techniques that can be classified into two large classes. The first one is, near field microscopy, where you have a scanning probe scanning over the sample, right, when the probe is very small, and because there is no objective lens, there is no diffraction, and therefore no diffraction limit applies. So it's very nice. And the second method is associated with nonlinear optics. Basically, you get your emitters. If you have like a fluorescent microscope, you get your individual emitters to light up, not all together, but one at a time. And then you can localize each emitter quite precisely. So these methods are very nice. There was a Nobel Prize in 2014 for one of these nonlinear methods. The problem is that they're all invasive, right? They involve some kind of active interaction with the sample. So the question is, can we avoid active interaction? Can we just do something passively with the light that's coming from the object? Can we do something different with it to improve the resolution? And of course, if we could, that would be huge, right? That would change the face of not only microscopy, but also astronomy and remote sensing and so on. All these fields of technology that have to do with imaging of objects that cannot be actively interacted with. But on the other hand, the Rayleigh criterion has been established 150 years ago. It's based on very solid science, so it doesn't look reasonable that we can beat it. But there's a very intelligent gentleman who you all know, Man-Kei Tsang, who said, yes, we can. But in order to do that, we need to change the very nature of the measurement. So usual measurement in traditional imaging is measuring intensity as a function of transverse position in the image plane. Yeah, so measure intensity as a function of transverse position. Instead, he said, let's measure correlations of field amplitude at different positions. Well, that's of course a very superficial description. What he proposed more specifically is the following. that we take the image field that arrives from our object, from our star, for example, and instead of measuring the intensity, we decompose it into a basis of transverse modes, which is typically Hermann-Gaussian modes, right? Then you measure the intensity of each mode and use the measurement result to reconstruct whatever information about the object we want. And what is shown is that the reconstruction will have a higher resolution than direct imaging, right? And I'll remind you that Hermann-Gaussian modes, well, I guess you're familiar with it. They look like this. And this next slide shows the intuition, why this works. Next few slides. So, well, this mode 0, 0 is just a Gaussian mode. Mode 0, 1 has this shape, and what's important, it's anti-symmetric, right? So this blob is positive, this blob is negative. So if you suppose you have a star and you measure the light from a star in the HG01 mode. Well, if your star is on the optical axis, then of course the image is symmetric. So an asymmetric mode will contain 0 photons. But if the star is slightly displaced, then be a small asymmetric component. So then you will have some light transmitted through this filter. Right? And now suppose you have two stars which are within the Rayleigh limit, so they're closer than the Rayleigh limit, they cannot be resolved from each other. But in this case, well, each of the stars will give some signal here, and therefore both stars will still give some signal as well, right? So you can use the signal to measure the distance between the two stars, and the distance will be much more precise than via direct measurement, which has been quantified, for example, via quantum Fisher information. Now again, why it's more precise, there is intuition as well. Look, these data, these two pictures are obtained from direct imaging, right? This is like a single slit, this is two slits. And you can see when two slits are very close, they coalesce, you cannot really tell anything like how far they are, right? But in this case, well, you have a single source versus two sources. In this case, you have no signal. In this case, you have some weak signal. Now, distinguishing between no signal and weak signal is much easier, even in the mathematical sense, than between an image and a slightly different image, right? So that's kind of the intuition why this technique works much better. Now, this is what Monkey has shown in their first paper. What we have shown in a subsequent paper is one can actually extend this whole thing to full imaging, right? So to extend to full imaging, you need to measure the intensity not only in Hermann-Gaussian 0-1 mode, but in multiple Hermann-Gaussian modes, HGMN, right? And then one can show that the amplitude in each HGMN mode is actually the mnth moment of the source field, right? So if we have some kind of amplitude distribution in the source field, right? You can measure, by measuring the amplitude in each Hermann-Gaussian mode, you measure the moment of this distribution. As we know from statistics, if we know the moment, if we know all moments of the distribution, we can reconstruct the distribution itself. Now, there are some complications that arise if you want to measure the intensity, rather if you measure in an incoherent fashion that I will not tell you about. Instead, let me show you this plot, which shows the resolution improvement as a function of the number of Hermann-Gaussian modes, right? So if you use just the 0th Hermann-Gaussian mode, you don't have any resolution improvement, and then as you increase this number, your resolution improves. So if you, for example, use 20 Hermann-Gaussian modes in each dimension, then your resolution will improve by about a factor of 3. Now, this is theory. In practice, when we try to do it in practice, we are facing a major problem. The problem is the following: how to filter our Hermann-Gaussian modes. It's easy to produce a certain Hermann-Gaussian mode, right? You can use a laser cavity, or you can use a spatial light modulator, but how would you filter one? How do you distinguish from other modes? In fact, it is possible using a spatial light modulator. There is even a company, a startup in France, which sells devices that do that. But these devices are not yet precise enough, and they can only distinguish modes of relatively low order. So it's quite difficult to do in practice. So the solution that we use is different. We use heterodyne detection. You see, in heterodyne detection, the detected signal corresponds to the signal light in the mode matching that of the local oscillator. So for example, if you prepare your local oscillator in HG01 mode, the photocurrent will tell you the amplitude of the HG01 component in the input signal. So this is a good alternative to mode sorting, very practical because, as I said, it's much easier to prepare Hermann-Gaussian modes than to sort them. And that's what we use here is our experiment. So we have two arms here. One arm is the local oscillator, so we prepare a local oscillator using a spatial light modulator. The second arm is the signal. We prepare our object here on a DMD. It's a macroscopic object, macroscopic image. I'll show it to you in the next slide. So that it's not yet proper microscopy. We have to artificially reduce the resolution by imposing the diffraction limit here by means of this iris, right? So we have a very small numerical aperture, right? And then we apply heterodyne detection, measure the signals, and reconstruct the object. Now the object is the university logo. Here it is. And well, you can compare the object with the point spread function. You can see that you can barely resolve the small print. Now, there is a dirty secret in that we don't really display the whole object, right? Because it's really, to decompose this object into Hermann-Gaussian modes, you need a lot of modes. So what we do is we actually displace pieces, the object piecewise, right? Like one blue frame at a time, right? And that in practice, that would correspond to scanning the image below the objective lens. So that's what we do. And well, before I show you the results, I should tell you that, well, I've shown you a nice mathematical theory, right? That you calculate, that you measure the content of each Hermann-Gaussian mode. This corresponds to the moment of the distribution. From the moments, you can reconstruct the image. In practice, this doesn't work at all. Because the theory assumes that there is that the local oscillator in a perfect Hermann-Gaussian mode, that the point spread function is perfectly Gaussian, that there is no dust, no aberrations, no misalignment at all. Right? So this math is completely useless. So instead, you use neural networks, which I guess brings me to the main point of the talk, that neural networks and optics can work well together. So in this case, the neural network would take the photocurrents as input, right? Take the photocurrents as input, and output the image. Right? And then we use a large number of objects, sample objects, to train the neural network, and then we show it objects that it had not seen previously, such as the university logo, and it would reconstruct the image. And the reconstruction looks like this. So this is our original object. This is what we can reconstruct by direct imaging, so affected by diffraction limit. And this is what we reconstruct by our method, by Hermann-Gaussian microscopy. You can see that the resolution is much higher. You can quantify the resolution improvement by showing our system these pairs of parallel lines. You can see that the direct imaging can only distinguish lines that are this far apart, whereas our new method can distinguish lines that are this far apart. So you get about a factor of 2 resolution, even better if you calculate differently. The same works in the incoherent regime. So if you apply, this is your original data. If you apply direct imaging, it looks like this. If you apply the reconstruction by our method, it looks like this. Again, significant resolution enhancement. Now, there is some theory which I don't have time to elaborate on whether there is real quantum advantage. So if okay, I should say a few words about this. You see, the question is how quantum it is, whether it's quantum optics or classical optics, right? The answer is that if light were classical, then this whole thing would not apply, because theoretically, you could simply deconvolve your image with the point spread function and obtain the perfect reconstruction of the image, no matter how large your point spread function is. In practice, it doesn't work because, well, even in theory, in reality, it doesn't work even in theory, because the points because the image is subject to shot noise, right? Shot noise will prevent you from doing deconvolution. As you know, deconvolution is very sensitive to noise. So that's the problem that arises, right? And then you really need like quite some very complex quantum calculation to determine whether the method has advantage compared to direct imaging. And basically, here we show that dependent on the diameter of the image, well, here's the quantum Fisher information, which tells the ultimate limit on the resolution. Here's the direct imaging, and here's the resolution obtained by different variations of Hermann-Gaussian microscopy. You can see that you can go above the diffraction. You can do better than diffraction limit and quite close to the quantum Fisher information limit. So to summarize this part of the talk, right? Again, our goal is to achieve resolution enhancement by means of linear-optical passive observation in the far field. Right? We have achieved that. However, there are two problems. Problem number, we want to really make it a practical microscopic tool, right? Practical imaging tool, in particular, practical microscopic tool. And we have not yet shown it with microscopic objects. To show it with microscopic objects, we need to solve two challenges. One challenge is, well, we need a training set, right? With DMD, of course, we could display in our DMD whatever we want. That will give us a training set. With microscopy, the training set would have to be something different. We don't yet know what it is. The second challenge is heterodyning. As I told you, heterodyning allows us to cut a lot of corners. The problem is the bandwidth of a heterodyne detector, right? It's limited by electronics. The bandwidth of a heterodyne detector is only like, a gigahertz. In regular fluorescent microscopy, the bandwidth of the light that you need to accommodate is like tens of nanometers. That means that you cannot use heterodyning. You need to use a proper mode sorter. And as I told you, this technology is not yet mature. So we need to address this challenge. With this, I thank you for listening.